Let's discuss when we have series that have both positive and negative terms potentially. And what's an example of this? Let's say k is 0 to infinity of minus 1 to the k divided by, let's say, k squared plus 1. Okay? Well, let's write out some terms to see what we are looking at here. When k equals 0, we have, let's see, minus 1 to the 0 is 1 over 1, so we have 1. And then when k equals 1, it's a negative 1 over 2. When k equals 2, it's positive. We have 1 over 5. When k equals 3, we have a negative again, and then it's over 10. When k equals 4, it's positive. We get 17. The next one, k equals 5. Maybe this will be the last one I write. This is negative again, 1 over, let's see, 5 squared, 26. And then this continues like this. What we see here is this is an example that falls under this category where we have series that have both positive and negative terms. Okay, and this one is a special type. Let me give you this definition. And this is what many of the ones we will see are in this section. This is what's called an alternating series. Alternating series, it means that the terms alternate in S-I-G-N and sign. Okay, so you go plus, minus, plus, minus, plus, minus. When you have an alternating series, the kth term, so in other words, the kth term is either minus 1 to the k times absolute value of ak, or the kth term is minus 1 to the k, say minus 1, absolute value of ak. Okay? This is an alternating series. If you have a series of all negative terms, well, certainly it would follow under this heading, but it's not alternating. If you have a series that goes plus, 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 minus, plus, plus, minus, 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 something like this, not alternating. Alternating series, every other term, it alternates in sign. So you go plus, minus, plus, minus, plus, minus. This is an alternating series. Okay? So many of the series we will see a minus 1 to the k or a minus 1 to the k minus 1 times something that is non-negative, for example. Okay, well, there are two different types of convergence, plus alternating series can also diverge. Okay, so we have more going on than we did when we only looked at non-negative series. So let me tell you a definition, and then I'm going to talk about this one. A series, sum of AK, converges what's called absolutely. So this is one type of convergence, converges absolutely, provided, well, the sum, absolute value of AK, converges. This is one type of convergence. Now, I will prove, maybe we'll do this example first, but I will call it a theorem for now, and I will prove it after this example. Theorem is if the sum of AK converges absolutely, I gotta move a little, absolutely, then the sum of AK converges. Okay? What this means is, if you have a series and you're able to show that when you take the absolute value, now this is a non-negative series, you take the absolute value of each term, okay? you show this converges, immediately you can conclude your series, something like this, converges, because if the absolute value of the series, take the absolute value term by term, if that series converges, by definition, this means the series converges absolutely, and this implies that the alternating series, or if it's just a series that has positive and negative terms, not necessarily alternating, but this implies the series converges, as I'll show in a moment. Okay, let's do this example. I'm going to use this idea before I actually prove it. And the proof is nice. I don't really prove a lot of things in this course. The only time is if it's constructive, so if we learn something in the process. And really, this proof of this blue theorem, it's a comparison test. So it's a very nice thing for us to see. Okay, now let's work with this example. Well, what happens with this series, which is in fact alternating? What happens when I look at some absolute value of AK? Well, we see here absolute value of AK is 1 over k squared plus 1. This series here, this converges. If I take this sum, so here, sum absolute value of AK converges. Why? Well, we have some choices. What am I going to do? The easiest thing for me, comparison. Okay, so as, well, we have 0 less than or equal to 1 over k squared plus 1 less than or equal to 1 over k squared. Why is this less than or equal to true? We have a larger denominator, smaller fraction. Okay, and then this series converges. It's a p series. Oh, I think I can fit p. Oh, maybe not. I'll just write p in the series here. P series, p equals 2, bigger than 1. And so by the comparison test, this series, 1 over k squared plus 1, converges. Okay? What does that say about the series I'm interested in? My conclusion here, this series, so we conclude then by literally this blue that's underneath, that this series, k equals 0 to infinity of minus 1 to the k over k squared plus 1, that this converges absolutely. Well, what's in the blue, I misspoke slightly. What's in the blue tells you that since you have absolute convergence, you know the series converges. But quite often when you have an alternating series, like this one is, you will be asked, does it converge? Absolutely. Does it converge? Well, there's another type which I will say. Or does it diverge? So this is one way it converges, and this implies the series itself converges. So we have figured out for this one, this series converges because the absolute value, term by term, take the absolute value, that series converges. Let's prove this statement. As I mentioned, it's a neat idea that uses comparison test, and it uses properties of convergent series. That's why we're going to do that in class. Now, what does this say? Another way we could have rephrased this is it says sum AK converges absolutely. So this is the hypothesis, right? It's another way we could have said this. So we are assuming here that the series, the sum of AK converges absolutely. And we will prove that in fact it converges. Okay, this is what we are doing here. And I mentioned this is just one type of convergence, and it's a very strong type of convergence because it implies the series itself converges. So now let's look at the proof. Well, first of all, to do this, let's consider what this here even is. What is the absolute value of AK? Well, we have two cases. It's either AK if AK is greater than or equal to 0, or this is minus AK if AK is less than 0, because, well, this just goes back to, for example, definition absolute value. If you put in a negative number, if AK itself is negative, you take the absolute value, it is negative, that negative and negative, this is now positive, right? Okay, well, what do we get from this? So then we get that on the one hand, well, here's what I'm going to compare, and then I will make my statement. AK, absolute value of AK plus AK. What can we say about this quantity right here? Okay, one possibility is AK is positive, in which case these two quantities are exactly the same, and we would get here. Okay, this holds when AK is positive, but certainly this is the biggest this can be. Okay, so this would be, we can do this, and this is definitely true. Okay. We have equality here when AK is positive, and then the other option is when AK is negative. When AK is negative, absolute value of AK is negative AK. Okay, so if we add here AK plus AK, absolute value of AK plus AK, well, this here, this part is minus AK. If you add minus AK to AK, you get 0. Okay, so we would have equals 0. It's equal when AK is negative, and every other time, of course, it's greater than or equal. So now let me erase this. So now I have inequalities that hold for all K. This one is equal when AK is negative. This one is equal when AK is positive, but both hold for every single AK, positive or negative. Okay, that just took a little bit of logic to think through with this definition here. But look what I have. I am setting myself up for a comparison test. Okay, so by the comparison test, as the sum 2 times absolute value of AK converges, ask yourself, why does this converge? Well, my assumption is that absolute value AK converges. Of course, then a constant times a convergence series will converge. We discussed, okay? So as this converges, you see the sum, this thing, absolute value AK plus AK converges. Okay? Well, I am trying to show the series AK itself, which I can't use comparison on because this series might be positive and negative, right? I'm trying to show it converges, but look what I have. I have the sum of AK in absolute value converges. This converges. And now all I have to do is then this series AK, which equals, it's this one, minus this one, right? Term by term is the difference. Of 2 convergent series. Therefore, this converges. Okay, so what we see here, it took a little trick, but really, my argument was a comparison test, and then properties of convergent series. If you have 2 convergent series, you add them, you get a convergent series. You take 2 convergent series, take their difference, convergent series. Okay, so what I have proved here is if you have a series that converges absolutely, then the series itself converges. Okay. Now I want to talk about another type of convergence that happens when you have alternating series, or more generally series with both positive and negative terms appearing. So one type is absolute convergence, and this implies the series itself converges. We will do more examples, but this isn't the only thing that can happen. Let's look at an example. Let's say 1 to infinity of minus 1 to the k over square root of k. This is alternating. If you look here, if you look at this, and I will put my indices here, although I could have left them off, but it's fine. Here, to infinity, this is 1 over the square root of k. This diverges. As it's a p-series, where p equals 1/2 less than or equal to 1. We will see, okay, but this series itself converges. Okay, and this is a different type of convergence because this series does not converge absolutely. Now, how can we see that this series converges? Okay, well, there's another test here, and this is the very last test we need to mention that's on that sheet that I gave you. It's called the alternating series test. Okay, so I will state it, I will use it here, and then I will talk about what this type of convergence is called. The alternating series test, what are the requirements? First of all, you need an alternating series. So you need that AK is minus 1 to the k, absolute value of AK, or you need that AK is minus 1 to the k minus 1, absolute value of AK. It must be alternating for the alternating series test. So we need this part, which says you are alternating, and then there are two more things. The first thing is that absolute value, AK plus 1, is strictly less than absolute value of AK. This would be for all k. This says that in absolute value, your terms is decreasing in absolute value. Okay. This is something that's usually pretty clear to check, but if you're unsure if your terms are decreasing in absolute value, number one, you could graph with your graphing calculator. Number two, you can take a derivative, right? If it happens to be a differentiable function, for example. And then finally, you need the limit as k goes to infinity, absolute value of AK equals 0. If you have both of these and you are alternating, then the conclusion is that the sum of AK converges. Now, if you have looked at that sheet I gave you with all the series and all the tests, I told you be careful with this because it does not distinguish which type of convergence you have. So for example, you will never conclude absolute convergence with this test. Maybe I'll put that in stars. This test, with this test, you will not conclude absolute convergence. Maybe the series converges absolutely. Maybe it does. Not this one, but some alternating series you are handed. Maybe it converges absolutely, but this test, the alternating series test, is not going to be the test that tells you that. This test only tells you if the series itself that is alternating converges or diverges. And then you will have to, for example, if you do this test first and you get converges, you have to then look at the series of absolute values of the terms and see if that converges or diverges to know if you are absolutely convergent. Okay, but this test is fairly easy to use because all you need to do is verify that your terms are decreasing in absolute value and that the limit of the terms is 0 and that you are alternating. Okay, so I'm going to have to erase. Let's use this test on this, and then I will mention what type of convergence this is called, where the absolute value diverges, but the series itself converges. Well, I've told you at this case, we will see it now with alternating series test. Okay. With this series, why? Okay, why? Well, absolute value of AK is 1 over the square root of K. First of all, it's alternating, right? We see a minus 1 to the K times absolute value of AK. But then we without a doubt have absolute value AK plus 1 is less than absolute value of AK because the denominator is growing. We have a fixed numerator. And so the terms are decreasing in absolute value here. And then we just need to calculate a limit as K goes to infinity, absolute value of AK. This is a limit as K goes to infinity of 1 over the square root of K. What is this limit? Well, the denominator is growing without bound. This limit is 0. Okay, so by the alternating series test, this series converges. Minus 1 to the K over the square root of K converges. And I mentioned this is the second type of convergence that we do not see. When you have non-negative series, there's one type of convergence, converges or diverges. I guess there's 2 types if you count diverges. You have convergence, you have divergence. And because the terms are already non-negative, if you took the absolute value of the terms, well, that's the series itself. So this notion of absolute convergence, it's no different than just convergence. But here, it's very different. This is the second type of convergence we see in this example. This series converges, but when I take the absolute value of the terms and look at that series, diverges. So let me now erase, at least erase a little bit, and I will mention what type of convergence this is. Okay. So definition, a series, I forgot my S. The sum of AK, this converges what's called conditionally provided. Well, the series itself converges, but, or and, maybe I will say, and the series where you look at the absolute value of the terms, this diverges. Diverges. Okay, so what have we shown here? Well, I'm erasing the work. But we just showed this series, K equals 1 to infinity minus 1 to the K over the square root K, that this converges conditionally. Okay, because, well, we showed that the absolute value of the series diverged, but alternating series test, the series itself with the minus 1 to the K, it converges. Let me get a better black marker. Okay, what's another example of a series that converges conditionally? And this is, we know this example is famous. It's about to get more famous. Okay, harmonic series. Except we need it alternating. Minus 1 to the k over k. This is called the alternating harmonic series. What happens here? Well, just think about it. This will converge conditionally. Let's talk about why. Well, absolute value of AK is 1 over k. If we sum 1 over k from 1 to infinity, maybe I should move out of the way, this diverges because this is the harmonic series. Diverges, or P series with P equals 1, less than or equal to 1, diverges. So this series, harmonic series, diverges. But think about the alternating series test. What do we need to check here? Certainly, we have this, and we have the limit as k goes to infinity, absolute value of AK, this is a limit, as k goes to infinity of 1 over k, this is 0. So by the alternating series test, I will abbreviate because I'm running out of space. Alternating series test here, the series itself, oh goodness, let me move, I really have no space. By the alternating series test, this series, 1 to infinity of minus 1 to the k over k, converges. It's what I just said, but I wanted to at least think about the alternating series test. Maybe you could have thought about this without me writing anything, but it's an example like this. The alternating harmonic series converges conditionally. And just like we quote that the harmonic series diverges, and that's a reason, you can just quote, if you see this, that alternating harmonic series converges conditionally, and that's just your reason. That is the alternating harmonic series. Let's talk about the third possibility. So far we have absolute convergence, conditional convergence, but alternating series can also diverge. And I'll do an example, and we will see why the alternating series diverges. Then I will make a chart and discuss if I have to figure out between absolute, conditional, those two types of convergence or divergence, which order or which strategy do I go about it. So let's see an example here where we have an alternating series that diverges. Something of this form, say k equals 1 to infinity of minus 1 to the k times 1, let's see, plus 1 over k squared. Something like this. Well, what's happening here? Let's look, first of all, this is definitely alternating because the absolute value of AK is 1 plus 1 over k squared, okay? Well, if we started thinking about the absolute value of AK, what do we notice? The limit as k goes to infinity, absolute value of AK, this is a limit as k goes to infinity of 1 plus 1 over k squared. This is 1. Well, in particular, the term test, right? This is not equal to 0. The term test would say the series absolute value, the sum absolute value of AK, this diverges. But I'm really just interested in this series. But having evaluated this limit, it helps me think about the limit of the terms of my alternating series. Okay, so then, this limit being 1, we know the limit as k goes to infinity of minus 1 to the k, absolute value of AK. Oh, well, let me just put the actual terms. Minus 1 to the k times 1 plus 1 over k squared. Okay, we saw stuff like this with sequences. We have a series that is approaching 1, and then we are taking this minus 1 to the k. So as k gets large, this thing is bouncing back and forth between 1 and minus 1. So this limit does not exist because it's oscillating. And this becomes a term test. When you have a limit of the terms and you get does not exist, or you get any number other than 0, you can conclude the series diverges by the term test. This series, the alternating series, k equals 1 to infinity minus 1 to the k, 1 plus 1 over k squared, diverges. Okay? So this is an example with diverges. Now, as I mentioned, let's make a chart, because we have, with alternating series, we have 3 possible things that can happen. And a lot of the homework or problems you will get on alternating series will ask you which of the 3. One possibility is absolute convergence. Okay. One possibility is conditional convergence. And the final possibility is divergence. We have these 3 different things that can happen when you have a series with positive and negative terms. Now, what does this mean? This one, it means the sum, absolute value of AK, converges. And then it follows that this also converges. We prove that. Okay. In this one, well, I'll start with actual series. This converges. Oh, I'm running out of space. And this diverges. But neither one follows from the other. The final one, the series itself, diverges, and it follows that here, an absolute value diverges. So I have color-coded these as to, if you're going to conclude, let me put a line under my headings. I have color-coded under here, so that if you are going to conclude absolute convergence or conditional convergence or divergence, what's in black is what you must show, okay, to be in this category. So here, if you show the absolute value, the sum, absolute value of AK converges, you're finished. You know you converge absolutely. Don't have to do an alternating series test. You're done, okay? Not too bad. On the other hand, if you know the series itself diverges, say term test, which will usually be the way that we show an alternating series diverges, okay? If you use a term test, the terms don't go to 0, the series itself diverges, again, done. Don't have to check this, okay? So these two, in a sense, are the easier in quotes, right? Because this is series, and it takes your mind time to get your brain wrapped around them, say. But you only have one thing to check to conclude absolute convergence. You only have one thing to check to conclude divergence, okay? But this middle case of conditional convergence, you must check both of these. You must show, in fact, diverges, and you must show that the series itself converges. Typically, how are you going to show an alternating series converges? Well, if you're not in this case, if you're just working directly, this would be alternating series test, okay? But what I mentioned in my comment about the alternating series test is it does not distinguish between this type of convergence and this type of convergence. because it never says anything about the absolute value. And I've seen students on tests before, they start off with an alternating series, do the alternating series test, and somehow conclude absolute convergence. Well, not by your test, okay? If you want to conclude this, you can't use the alternating series test. Take the absolute value, use comparison, limit comparison, integral test, or ratio or root. The conclusions of those are absolute convergence, and I will do at least one like that, okay? But this case is kind of the hardest because you actually have two things to verify. Let's start with this example. We see an alternating series because this is minus 1 to the k. Well, if I look at the absolute value, this is 10 to the k over k plus 1 factorial. Right? If you think quickly in your head, go in my order I mentioned. If you think quickly in your head what's happening to the terms, we have factorials in the denominator, we have exponentials in the numerator. Factorial grows a lot faster than exponentials. The terms are going to 0. Okay, but if we look at this, well, we see factorials. This is telling us ratio test. Okay, so this is what I'm going to do here is a ratio test. I'm going to look at absolute value ak plus 1 over ak. Now, if you remember, I put it in parentheses, but the conclusion of the ratio test, if you get that the limit is less than 1, the conclusion is absolute convergence. Okay, so what I will get out of this, if I calculate the limit, which I will, and if I get less than 1, which I will, my conclusion will be absolute convergence. And then I will be done. I don't have to check with an alternating series test, for example. Okay, well, in absolute value, what happens, this minus 1 to the k part becomes a positive 1. So this is 10 to the k plus 1 over, well, it's going to be k plus 2 factorial. When I take the kth term, and let's say well, maybe I'll write it underneath like this. I was going to go ahead and invert and multiply, but I'll do that now. This will be 10 to the k plus 1 over 10 to the k, and then times k plus 1 factorial over k plus 2 factorial is in the denominator. You see, k plus 2 factorial, we have practiced similar, right? K plus 2 factorial is k plus 2 times k plus 1 factorial, like this. So this simplifies to just 1 over k plus 2. So when I simplify this, this quotient and product, these terms, I have a 10 in the numerator, I have a k plus 2 in the denominator, and now I take a limit as k goes to infinity, a limit as k goes to infinity, absolute value ak plus 1 over ak. This is a limit as k goes to infinity of 10 over k plus 2, which is 0. This is less than 1, by the ratio test. My series, the sum, k equals 0 to infinity minus 1, oh, I'll put the 10, minus 10 to the k over k plus 1 factorial converges absolutely. Okay, now let's do another example. Well, I should mention we are done, right? I have figured out its absolute convergence of the three things that can possibly happen. How about something like this? You notice I couldn't start out 1 here with my sum because the natural log of 1 is undefined. Well, this is definitely alternating because natural log, it goes to the point 1, 0, and like this. So as long as we are bigger than 1, natural log is positive, then we have this minus 1 to the k. Okay. So absolute value of AK here is 1 over ln k. Now what am I going to do here? How am I going to figure out? So question, does this converge? So question, does this converge? Question, does this converge? K equals 2 to infinity of 1 over ln k. What happens? Because if I do my first pass at the terms are going to 0. And so I can't use the term test. So then I would say, okay, take the absolute value, take the sum, absolute value of the terms I should say, and then take the sum. Does this converge? Well, what happens here, can we integrate this? No, I mean, 1 over ln k is one of the functions that does not have an elementary antiderivative. So trying to calculate an improper integral here and do an integral test, this would be challenging. Well, we can use comparison, and I'm going to have to use the fact. So I'm going to use the fact, note that the natural log is strictly less than k. Okay. Of course, this came up in our growth rates that as you get very large, this grows significantly slower than, but this is true. This is true generally, that the natural log is less than k. Well, okay, I will say 4k bigger than or equal to 2. The only ones that matter here, okay? I'm looking at 1 over, so I have the following. 1 over k less than or equal to 1 over ln k. You see, if this is less than this, then when you take 1 over, it's going to be bigger. So 1 over ln k is bigger than 1 over k because the denominator is smaller. Okay, and the sum of 1 over k diverges, it's harmonic. Therefore, by the comparison test, we are term by term bigger than something diverging. The sum k equals 2 to infinity 1 over ln k diverges. So, do we have an answer here? We're not finished. All we know is that this series does not converge absolutely. Now we can apply or use the alternating series test. Okay? So we know we are not in this. No, where did I have absolute convergence? Over here. It is over here. Now for alternating series test, well, I know the absolute value of AK is 1 over ln k. I've already certainly commented on that. And this definitely satisfies that absolute value AK plus 1 is less than absolute value of AK because, while the natural log is growing, 1 over it would be decreasing. And then the limit as k goes to infinity of 1 over ln k, this is 0. Okay, so by the alternating series test, my series, the original series, k equals, oops, not 1, 2 to infinity, minus 1 to the k over ln k, this converges. Okay, but now we need to make our final conclusion. If we are asked, does the series converge absolutely, conditionally, or diverges? Let's look at what we have shown. We have shown, if you look at the absolute value and take the sum, well, that series diverges. Here, comparison test. But the series itself converges, alternating series test. So this series converges conditionally. Here, converges conditionally. Let's do one more example of an alternating series, and it's this one. Again, we have a natural log in the denominator, but there's more things down here. We have a k times ln k cubed, and again my sum goes from 2 to infinity. If I quickly glance at the terms, well, the terms are going to 0 because the denominator is growing without bound, and I have a minus 1 to the k part. The terms are going to 0. I can't use the term test here. It would be inconclusive. Then if I look at the absolute value of ak, it is 1 over k ln k cubed. Now, this is what I always try next, right? If the terms are going to 0, I look at the absolute value, see if that converges. If I look here, how am I going to figure out if this converges or diverges? Integral test, right? Because I have an inside function, I see a multiple of its derivative. Very natural to look at the integral test here. Okay, so if we consider f of x, which is 1 over x ln x cubed, this is, well, it's continuous, it's non-negative, and it is decreasing on to infinity. It's decreasing because the denominator is growing, right, and the numerator is fixed. Okay, so I may use the integral test. So let's calculate an integral from 2 to infinity of 1 over x ln x cubed dx. This is substitution. But maybe before I begin, it's quite important to understand we're doing the integral test on, well, where we took the absolute value of the terms, because with a minus 1 to the k or a minus 1 to the k minus 1, cannot use the integral test because the function, well, it's not continuous and it's not non-negative. So the integral test, comparison test, limit comparison test, none of those can you use on an alternating series. You could use it on, for instance, you take the absolute value of the terms, look at that series, and that's what we do in some of our examples, but not directly on terms like this. Okay, that was a comment. Now let's get back to this integral. Okay, we have u is ln x, du 1 over x dx. We have exactly 1 over x dx in our integral. Then, oh, I need to write, this is a limit. As b goes to infinity, an integral from 2 to b of 1 over x ln x cubed dx. Okay? So as I say, when we calculate integrals, it's a definite integral, then it's a limit. Let's change our bounds. When x equals 2, u is ln 2. When x equals b, u is ln b. So here is all of my side work for the substitution. Okay? Then, this is a limit. As b goes to infinity, the integral, we go from ln 2 to ln b. And then my integrand becomes, let's see, u to the minus 3 du. Okay, so let's integrate. Well, this is a limit. As b goes to infinity, okay, we have add a power, divide by the higher power, evaluated between ln 2 and ln b. This is a limit as b goes to infinity of, well, this is really a squared in the denominator, so this is going to be negative 1 over 2 ln b, ln b squared, and then it's going to be minus the minus of plus 1 over 2 ln 2 squared. Okay? Finally, we evaluate the limit. Natural log grows without bound. 1 over will go to 0. This term goes to 0. This term has no b. So this limit is 1 over 2 ln 2 quantity squared, which says that my improper integral converges. I got a number. Okay? By the integral test, this series, which is the one that is k equals 2 to infinity of, we have the positive terms, so the absolute value of the terms, this converges. So now we go back and we make our conclusion about the alternating series. We have shown using the integral test that the absolute value, or take the absolute value, take the sum, this converges. That means that this converges absolutely. When we are in this situation, then we don't have to run through an alternating series test to say anything else. Once you know it converges absolutely, then the series itself converges, and you have classified which type of convergence happens here. Okay? Okay, so now is the time if you want more examples, which, well, people tend to struggle with absolute and conditional convergence and divergence. So here you can look, right? See more, practice more, and hopefully master this material.